Talking about aerodynamics to
Yes.
make it a bit more generalistic. Ryo is assistant professor or
Fixed time.
a fixed time assistant professor at Tokyo University of Science. He got his PhD in 2023, double degree between Japan, University of Osaka, and Lyon, the École Centrale.
Echo center.
He's working on computational fluid dynamics, turbulence, multiflows, so on and so forth. Not really. You're not.
Not on multiphase flow,
Okay.
but on the fundamental aspects of turbulence.
Fundamental aspects of turbulence. Okay. And Yusuke is a postdoctoral research fellow in Nagoya University now. He also did his PhD in Osaka University. He finished in 2024. He's a bit more junior. And he's also working on computational fluid dynamics, turbulence. In your case, yes, multiflow. No? Okay, very wrong.
I know.
Sorry, I'm an outsider. And he's going to be talking about, or the title of his talk is How Universal Are Lagrangian Statistics of Turbulence. So quite fundamental as well. So, floor is yours now.
Yeah.
I'm not going to be able to stay until the end, so Alberto will take over the round of questions. Okay, sorry for that. I have to go for a meeting. Okay.
Yes.
Welcome.
Yes.
And floor is yours.
Okay. Okay, so thank you very much for your introduction, and thank you for having me for the very first seminar of this academic year. So my name is Ryo Araki. I was born in Kyoto and studied in Osaka up to my master's degree at Osaka University, and then I did my PhD in École Centrale de Lyon and Osaka University as a double degree program. And since 2023, October, I have been working at Tokyo University of Science as an assistant professor but fixed term. So it's more of a postdoc, long postdoc with some teaching duties. So I'm definitely looking for next position. And actually, I have been working on various projects from very fundamental to a little bit more application oriented. And today I would like to talk you through about this part 3. So how can we perform causality-based model decomposition of flows with unsteady base flow? So which is actually quite aerospace science-oriented project. So I have been working with many people, including Alberto Ferramartin. And today I'm going to present a project which is a collaboration with Professor Kai Fukami at Tokyo University. I think he's only 30 years old, but he is already associate professor in that institution. And I think some of you have recognized his name because he's been writing a lot of papers on machine learning, turbulence, data-driven fluid dynamics things. Okay, so causal mode decomposition of separated aerodynamic flows. So I'd like to start with the concept of extreme aerodynamics, which I have never heard of before this collaboration. So extreme aerodynamic encounters or extreme aerodynamics is something you encounter in urban environment on like drones or helicopters or small airplanes. We tend to have much strong gusts, strong winds in, for example, in urban areas in compared to the rural areas. And it is very important to control the aircraft so that it will not fall down. So actually, Fukami-san has been working on this project in order to construct a low-dimensional model of, for example, on the right-hand side, I show a picture of wing, which encounters a very strong gust. And what will happen? How does the aerodynamic force response to such a gust? And today, what we are going to discuss, okay, so still a very introductory part. So there are, the model decomposition is quite fundamental, common in the field of fluid dynamics. Maybe you have heard some of the keywords on this slide, such as proper orthogonal decomposition or dynamic mode decomposition in order to suppress the information of the flow. Based on, for example, proper orthogonal decomposition or POD try to reconstruct the energy of the flow by using minimum number of orthogonal bases. And there are operator-based approaches such as stability analysis and resolvent analysis. And the figure is taken from Professor Tyler's review article in 2017. But the important point here is that most of these methods assumes steady base flow. And we can't really deal with the very transient or unsteady flows. So what I'm going to describe you, what I'm going to tell you is how can we perform model decomposition of flows with unsteady base flow. And to tackle this problem, we employ some concepts from information theory. So have you ever heard the term like Shannon entropy or mutual information? So these are quite common. If you have been working on machine learning, then these quantities, tend to happen when you construct your network or evaluate the, and update your weight in the neural network, for example. So the Shannon entropy, h of x, can be understood as the average uncertainty of a random variable, capital X. So that minus natural log of px is regarded as an information of a certain event, small x, out of the random variable, capital X. And the mutual information can be understood as the nonlinear correlation between two random variables, x and y. We often use that schematic, like a Venn diagram. So there are two circles correspond to the Shannon entropy of random variables x and y, and the overlapped region is the mutual information of two random variables. So we will use this quantity throughout my presentation. So what we do is actually we borrow the idea, we use the idea from a recent paper by Arans and Lozano-Duran, happen to be my collaborator as well, the concept called informative mode decomposition, which is a framework to decompose a source variable to extract an informative component from the source variable, which contribute to a future target variable. So if you notice the argument here, the source variable is, is defined on both space and time. And here, for the simplicity, we consider scalar target variable in the future. And this is the formulation. So the source variable, q of x and t, is decomposed into two components, qi and qr. And qi, the subscript I, stands for the informative, and r stands for residual, or something left. And we perform the decomposition such that the mutual information or the nonlinear correlation between two components are zero, which means they are statistically independent. And the mutual information between the future target variable and the informative component is maximized. So that's how we can construct this informative mode decomposition. Okay, so by using this decomposition and by imposing this decomposition into the neural network called deep sigmoidal flow, we construct a machine learning framework in order to extract the informative component from the flow. So this, the definition of the weight consists of two terms. The first one is reconstruction. So the informative mode needs to be as close as the original source variable as possible, while the second term imposes a constraint stating that the residual or the non-informative mode and the informative mode needs to be statistically independent. So this is the weight function inserted or embedded in the machine learning network. And now I'm going to present several examples of how this informative mode decomposition, machine learning, data-driven informative mode decomposition works against, for example, the first example is two-dimensional separated flow with an extremely strong gust. So if you look at the video, the gust approaches the wing and it pinches off and it creates the separated flow. So the gust is defined like this. And we employ the vorticity field as a source variable, and we set future lift coefficient, a lift coefficient at t plus delta t as a target variable. So we want to extract what is the informative vorticity component or vorticity structure in the flow in respect with the future lift coefficient. And this is a result. So on top of the slide, I show a time series of lift coefficient. The gray thick line corresponds to the lift response where there is no gust. And orange, red curves corresponds to the lift coefficient response to weaker and stronger gusts. And in the latter half of this slide, there are multiple visualizations. So these 4 visualizations, 4 columns corresponds to these 4, these circles. The instances are represented by these circles in the time series. And on the first row, I show the input or the original vorticity field. And on the second row, there's a IMD, which stands for informative mode decomposition. So the causal vortex structures. And obviously, the orange panel corresponds to weaker gust, and red panel corresponds to stronger gust. And what you can infer from this figure is that, for example, if you look at this panel, the gust does not appear as informative at this instance, which corresponds to this minus t equals to minus 0.98. And actually t equals 0 corresponds to the instance where the gust actually reaches the wing. However, when the gust approaches and almost arrives at the wing, then this gust is classified as informative or causal for the future lift response, and so on. Okay, so the gust is informative for CL at t plus t plus delta t when it reaches the airfoil. But obviously, it depends on the choice of delta t. So for example, in this experiment, in this numerical experiment, the time delay delta t is said to be 0.0085 in terms of the washout time unit. So what will happen if we vary this delta t? So that's next experiment. So the configuration is same as the previous one, but here we changed the value of delta t. So what we have learned from here is that when delta t is very small, or in other words, when we try to identify the causal vertical structures for very near future lift coefficient, then the nearby gust is classified as informative. And when we increase the delta t, in other words, when we want to identify the causal structures for more distant future lift response, then faraway gust gets classified as informative, so it matches to our intuition. So this informative mode decomposition extracts the time-varying causality. So I think it is more or less matched to our intuition, so we want to proceed with some more non-trivial features of this informative mode decomposition. So the next example is this noisy PAV experiments. So there's a 2D flow set in a domain, and there's a transverse gust going from left to right in that visualization. And apparently, the measurement is quite noisy. Some of you have been working on PIV, you know that it is very difficult to denoise the PIV experiments. So what will happen in this case? And the other configurations are quite same as the previous ones. So the source variable is vortex field, and target variable is future lift coefficient. So we want to identify what kind of vertical structures are causal or informative against the future lift response. And this is what I've got. So the gust is informative when it reaches the wing. Obviously, it depends on the delta t, but it is same as the previous example. But what is striking here is that informative mode is denoised. And actually, it is a really nice feature when it comes to the model decomposition of flows, but obviously, because the conventional methods tend to be very sensitive to the noise. However, by employing the information theoretic framework, we can identify the causal vertical structures from noisy vorticity field. So that's, I think, very interesting perspective, interesting characteristics of this informative mode decomposition. And the final example is this 3-dimensional turbulent wake of this NACA NACA 0012 wing at much higher Reynolds numbers in compared to the wing numerical experiments. So the domain is periodic in span-wise order, and the numerical simulation was conducted by well-established LAS solvers. And the other configurations are as same as the previous ones. So the source variable is vorticity field, and target variable is future lift coefficient. Okay, so this is what we've got. So as same as the previous examples, on top I show the time series of lift coefficient, and these circles corresponds to 4 instances shown in the bottom half of this slide. And this center row corresponds to the original vorticity field, which has variety of scales, which is obviously the characteristics of turbulence. And this third row corresponds to the informative mode, causal mode, to the future lift coefficient. And what we notice here is that without explicitly imposing any characteristic length scale in the machine learning architecture, this informative mode decomposition identifies the choral vortices or large-scale vortices as informative or causal to the future lift response, which is I think also a really nice feature. And obviously we need to try various different physical quantities to see how the causal structures are different for different target quantities, but this is at the moment what we've got. And okay, so this is a summary of my presentation. So what we have conducted is causality-based model decomposition on extreme aerodynamic flows. And this informative model decomposition is able to extract causal vortical structures in respect to the future lift response. And this framework is quite general. So at the moment, in this study, we restrict ourselves to the relationship between the vorticity field and future lift response. But this framework can be applied to any quantity you want. So we are really looking forward to explore different physical quantities in different flow configurations, and so on and so forth. So the conclusion, take-home message is this. I think there's a promising feature with the causality-based flow control and modeling. Thank you very much.
Thank you for the... Vale, ahora no. Vale. Thank you for the talk, Ryo. Very nice. So now we have plenty of time for questions. People are here to go.
Very impressive presentation. And I have some questions. So the idea of the informative model decomposition is to, I think, maximize the mutual information of the informative mode and the target, and minimize the residual mode and
Okay. If you can start the...
Yeah, you can repeat your question.
in the meantime, minimize the residual mode, the mutual information of the residual mode and the target.
Yes.
Okay. So in your work, you use lift coefficients as a target.
Mm-hmm.
I mean, in the original paper of Lozano, Professor Lozano, they use the informative mode decomposition to decompose the turbulent channel flow based on the wall surface shear stress.
Yes.
And have you tried for the gas encounter case? You tried I don't know if you tried the informative mode decomposition based on surface measurements like surface pressure.
We haven't done that. But we are discussing that we should try, various physical quantities. But at the moment, this is pretty much ongoing project, and we have just published first paper by investigating the relationship between vorticity field and lift response. But it would be very important to extend this study to surface quantities, because otherwise you can't apply this framework to control of the flow. So it would be very interesting. And this 2024 paper, that's very nice. Yeah, we actually applied this methodology to aerodynamic flows.
And I think Because for lift coefficients, it's integral.
Exactly.
Yeah. There
Exactly.
will be some loss of information from.
Yeah, exactly. So I'm sorry. Actually, here is this QI depends on both space and time. I'm sorry, there's a mistake. But yes, in this study, we constrained the target variable to be a scalar quantity, so integrated over the whole domain. Otherwise, the curse of dimensionality, obviously.
Yeah,
So it will be very difficult for this machine learning stuff to converge the output. So that's why we restrict the target variable to be a scalar. But obviously, we, or more specifically, a very talented undergraduate student in Professor Fukami's lab, has been working on extending this framework to, how to say, non-local. For non-local quantities. Sorry. Yes.
Yeah. And for the delta t, the time variables, because how do you choose a proper delta t for it?
Yeah, this is more of a numerical experiment.
Yeah.
So we varied delta t to see how it depends on. So in future, if we want to apply this methodology for specific purposes for flow control, then we need to choose appropriate delta t, obviously. But again, this is developing study in progress. So at the moment, we varied delta t to see.
Find a peak,
Yeah, possibly a peak of what?
A peak of mutual information.
Yes, it can be possible. Yeah, it can be possible. Yes.
And my second question is about you also conduct this on experimental data sets.
Exactly, an open source data set.
Oh, wow. It's impressive. And my question is...
That's actually the request from the referee.
Yeah.
Try noisy data.
And my question is about, because for the information theory, if we for experimental data, we got noise adding as the time proceed. So the information, the Shannon entropy is not equilibrium. It will grow in time. And so how do you, that will introduce some issues, I think, for the casualty and mutual information calculation. I don't know how do you deal with this.
Okay. I think you mentioned about the
there's some information leakage
error in the measurement.
In
the experimental data set.
Yeah. The noise introduced by measurement. So there the information, the whole amount of information entropy is not a, it grows.
Obviously, yes. So we haven't considered, for example, the information leak or something, but I find this feature, denoising effect of this informative mode decomposition quite intriguing. But we need to think about that.
Okay, I'm asking because for the causality analysis based on information theory, it's a main issue for experimental data set.
Some unobserved variables, unobserved degrees of freedom. I think you mentioned about the previous paper by Losang-Zhang and others, right? We can discuss later. Yes, but these are quite different frameworks, so we haven't considered any information leak or related things in this project. But I have been working on that project as well, so we can discuss later.
Okay. Thank you very much.
That's good. Maybe you can get together later. And
yes.
Seems like there is ground for collaboration. So you have a...
Well, thank you for the talk, Araki. It was super clear, very nice and clear talk. I have one question about the method itself, about the two slides that you just saw before. So when you define the mutual information, here, everything here is probability space, normal space. This is the composition, both I, the target variable, and the entropy, and the fact that the residual or non-informative space should be orthogonal is in information space.
Exactly.
But when you go to how you optimize your neural network, you have a mixed norm. You have, can you go to the next slide, if you don't mind? So here, the left part, the reconstruction part, is an energy. Well, not energy if you are using vorticity, but then it's an entropy. That's a norm over the physical space. Whereas beta times the information is an information constraint.
Okay, yes.
So it's like a mixed norm, right? I thought part of the idea
Exactly.
behind this causality thing was leaving energy and entropy aside, right?
Okay, I think I got your point. So the first time is physical quantity, and the second term is indeed some informative quantities. Okay, I need to check the original paper, and because this is implemented by Fukami-san, and I'm not very familiar with machine learning architecture, so I will get back to you once I checked the original manuscript. Yeah, I do not. Maybe. I'm sorry. I will get back to you on this point.
No,
Yes.
don't worry.
Any more questions? Okay, I have one myself, very nice talk. And it maybe goes along a little bit of what Miguel suggested. I'm curious of what you have a decomposition that is not linear, right?
Mm-hmm.
What does a mode mean? You talk about modes.
Mode. What does the mode mean?
So I have in mind this idea that of a linear operator, and then you decompose it, and you can do the summation of some coefficient plus the mode function. But here that doesn't exist, right? So how do you get the modes? How do you know what I mean?
Well, obviously, there are plenty of studies for conventional model decomposition analysis. And what does the mode mean?
So how do you get it? Because you get the neural network it gives you like it's used for prediction, right? The neural network itself. You use it to predict, but then you want to figure out what is the structure that is sort of being predicted. That is what you get when you get the mode, right? Or maybe I didn't get it.
Sorry, are you talking about the characteristics of this extracted mode, or
Yeah. How do you get? Because you have only one mode, you have many of them. You're only getting one now, but you could get many, or.
Okay. Yes.
So by looking at the architecture, it seems like you're getting only one, right?
Yes.
On Q, but you could get many of them, right?
But we can get many more modes
Yeah.
by extending this framework. And actually, the final figure of the published paper is about that point. Okay, so I will get back to you as well on that point.
Okay.
Yes.
And so related to that question, you think you can turn this into a linear problem and get something more like a proper orthonormal decomposition, but with information? It's also a very long shot, but I am wondering.
Yes, we haven't
It's not a good idea to make
investigated into such kind of problems, but we indeed compared the modes extracted by this decomposition from the POD results. So yes, maybe I can show you the paper. Okay, so although I didn't include this final result, but yes, yeah, we can identify the second IMD mode, third IMD mode, and so on and so forth. And this left-hand side shows how much energy is reconstructed from the decomposition, or something like that. And the key point here is that in POD analysis, you've got more or less like symmetric modes, but in this informative mode decomposition, you've got more asymmetric structure. So it should more correctly capture the dynamics. So that's what we concluded in this paper. Okay.
Yeah, I'll take a look at it.
Yes,
reach
thank
back.
you.
Okay, so no more questions. Then we can thank the speaker again.
Thank you very much.